Okay, so let's start another section. It's 4.1. It's called Divisibility. So divisibility, 4.1 here. Divisibility. So what does it mean for an integer to divide another one formally? Well, let's define it. Okay? So the formal definition is this. Let A and B be integers. Okay? Then A divides B if B is a multiple of A. In other words, if there's another integer that multiplies A to B. If there exists another integer, say C, such that AC is B. Now when this happens, instead of write A divides B or D divides F and E divides R, instead of keep writing this, we make a symbol up for it. Okay? So when some integer A divides some other integer B, we write an A with a straight up and down line and then a B. Okay? So that symbol communicates A divides B. For example, 2 divides 10. Why? Since there's another integer, 5, that multiplies to 10. So you can see the definition is satisfied. Okay? With that being said, now you can prove bunches of stuff about divisibility. Just countless things. And the first thing is Theorem 1 in 4.1. So Theorem 1 in 4.1 goes like this. Let A, B, and C be integers. Okay? Then, thing 1 that you can prove. If A divides B, and now you can see I'm using my notation here, and A divides C, then A divides B plus C. So we want to prove that, of course. Thing 2, if A divides B, then A divides any multiple of B, BC, for example. And thing 3, division is transitive. In other words, if A divides B and B divides C, then A divides C. Okay, so those are the 3 parts to the theorem. Let's prove them. So let's go for thing 1. So proof. Okay, for 1. To prove 1, we know A divides B and A divides C. And so we have to use the definition of division up here and exploit that to show A divides B plus C. So you could say since A divides B and A divides C, that was given to us here, there exists some integers. I'll call the first one K, maybe the second one L. We don't know they'll be the same integer, so you need to use different letters in Z such that AK is B and AL is C. Okay? So I've just exploited that A divides B and A divides C through this definition up here. And now let's try to prove A divides B plus C. Okay? Well, if you look at b plus c, then if you look at b plus c, what can you say that's equal to? Well, you can replace this in for the b, because it is b, and you can replace this in for the c, because it is c. I mean, what else? So you could say that's AK plus AL. What can you say that's equal to? Well, notice now you can factor out an A. So you can say that's A times K plus L. And you've just realized that B plus C is a multiple of A. But then by this definition up here, A divides B plus C, and the proof is done. But anyway, let's say it and wrap it up. So you could say since, just have to make sure we explain why that's an integer under here. Since K and L are integers, we know K plus L is an integer. So thus, B plus C really is a multiple, an integer multiple of A. So thus, A divides B plus C. Let's prove thing 2. Now, thing 2 says this. Okay? A divides B, show A divides BC. Okay, so for 2, since A divides B, again, there exists an integer K such that AK is B. Then if you just take this equation and multiply both sides by C, you could say then AKC would be equal to BC. And so you've just found an integer that multiplies A to BC. As long as you can explain why that's an integer, you now have A dividing BC by the definition just a page ago. So since, and again it's since K and also C were integers, we know KC is an integer. Thus, A divides BC. And for the final thing, part 3, let's prove that. Part 3 says this. If A divides B and B divides C, show A divides C. Yeah? In other words, division is transitive. Let's prove it. So finally, for 3, since A divides B and B divides C, there exists 2 integers, one for each division. We don't know they'll be the same, so you have to use different letters. I'll call the first one K, the second one L, in Z, such that for this one, AK is B. For this one, BL is C. And BL is C. Okay? That's me exploiting these 2 givens. Okay, now I have to show A divides C. So I'm going to have a look at C and see if I can show it's a multiple of A. Now, if you look at C, what can you say it's equal to? Well, from here, it's BL. But what can you say now that's equal to? Well, you can replace the B, this in for the B, because it is B right here. And finally get A and C connected. So you can say that's AKL. So you've just discovered that C really is a multiple of A. As long as you can explain why that's an integer, the proof is done. So you could say since K and L are integers, we know KL is an integer. Therefore, this equality says A divides C. Therefore, A divides C. And the theorem's done. Okay, so realize those three weapons. Yeah? If an integer divides two integers, then it divides their sum. That's thing one. If an integer divides another integer, then it divides any multiple of it. That's thing two. And thing three, division is transitive. If A divides B and B divides C, then A divides C. Okay? Now I'm going to describe another relationship that involves division of integers. It's called modularity. So it's a definition. Okay? Definition. Suppose I have three integers. Let A, B, and M be integers, such that, say, M is bigger than or equal to 1. Okay? Then we say A and B are congruent modulo M. Let's write that. Then A is congruent to B modulo M. So that's the phrase, baby, that we're defining. Okay? If M divides their difference in this order. So we say A is congruent to B modulo M if M divides A minus B. Okay? Now this is a long phrase to keep saying. So again, we invent a symbol for it. Okay? We write A is congruent to B mod M when this happens. Like this. For example, very easy. For example, 7 is congruent to 3, modulo 2, mod 2. Why? Since 2 divides their difference. Since 2 divides 7 minus 3, because that's 4. Another example, minus 8 is congruent to 4, mod 3. Why? Got to check the definition up here. Since 3 divides their difference. Since 3 divides minus 8 minus 4, because that's minus 12. And 3 divides minus 12. Goes in minus 4 times. Okay. One more. 21 is congruent to 1, mod 5. Why? Since 5 divides their difference. Again, we're going through the definition up here. Since 5 divides 21 minus 1, because that's 20. And 5 divides 20. Goes in 4 times. Okay, so that's what modularity is. And now you can prove a theorem. Okay? So let's try to prove a theorem. So this is theorem, I don't know what the number of this is. I think it's theorem 5 in the book. I think it's theorem 5 and 4-1. Goes like this. Let A, B, C, D, and M be integers. Okay? Such that, let's keep going now, such that, let's put a such that symbol there, such that A is congruent to B modulo M, and C is congruent to D modulo M. Okay? Then you can prove two things. Okay? Then, thing one, A plus C is congruent to B plus D modulo M. See, it's almost like we're adding both sides here. Isn't that cool? And thing two, you can multiply both sides, like sides. AC is congruent to BD modulo M. Okay, let's prove it. So some of your homework problems will talk about modularity. Others will talk about divisibility. Okay? And ask you to prove different things. Well, let's prove this. Maybe you'll catch a clue. Anyway, let's prove it. Okay, let's start with thing one. For one, again, I have to exploit what I'm given, otherwise I'll never prove anything. So I have to exploit that he said A was congruent to B mod M, and C was congruent to D mod M. Okay? So let's exploit that. Since A is congruent to B mod M, because he said it was, and C was congruent to D mod M, we know M divides those differences. In other words, M divides A minus B, and M divides C minus D, because that was the definition a page ago. Now, 2 pages ago, I know the definition of division. That means both these numbers are a multiple of them. I don't know the multiples are the same, so I have to use different letters. So thus, I'll use K and L again. Why not? There exist 2 integers, K and L, in Z, such that for the first division, MK is A minus B, and for the second division, ML is C minus D. Okay, so I've exploited the 2 things that he gave me. Yeah, these 2 things here. And now I have to prove these 2 things here. Let's start with the first thing. That's what we're talking about now. Thing 1. I have to show A plus C is congruent to B plus D mod M. So I have to show M divides their difference. So I have to show their difference is a multiple of M. I'm going to look at their difference right now. So you can say now, if you look at the difference of these 2 numbers, that one and that one, that would look like this. A plus C minus, in parentheses, B plus D. What can you say that's equal? That would look like this. A plus C minus B plus D. What can you say that's equal to? We'll drag the minus through. That would be A plus C minus B minus D. What can you say that's equal to? Well, I can rearrange this because you can add numbers in any order. So I can write this as, I can put these 2 together and these 2 together. So I can write this as A minus B plus C minus D. What can I say that's equal to? Anyway, now obviously I can use this box for the A minus B and put it there. And obviously now I can use this as a weapon for the C minus D and put it there. So I can write this as MK plus ML. And it should be obvious. What can I do now? Obviously, I can factor out an M. It doesn't take a genius, folks. So I can factor out an M and write it this way. And so you've just discovered that their difference is a multiple of m. That means m divides their difference. That means they're congruent mod m. And thing 1 is proven. Okay, let's circle that. Okay? So as long as you explain why that's an integer, then you have it. Okay? And it is because k and l were integers here. When you add two integers, you always get an integer. Okay? So since k and l were integers, we know k plus l is an integer. So you can say, thus, from this equality in the big bubble, m divides their difference. M divides a plus c minus b plus d. And so they're congruent mod m by the definition on the previous page. And so a plus c really is congruent to b plus d mod m. And that gives thing 1. Okay. That gives thing 1. Okay. Now let's prove thing 2. AC is congruent to BD mod M. Well, I'd have to show M divides their difference. So I'm going to look at their difference and see if I can show it's a multiple of M. For 2, let's look at AC minus BD. What can we say that's equal to? Well, if you look back here at these two circles here, for these differences, I can use those as weapons again, just like I did here. Okay? I can use this circle to replace A here. And I can use this circle to replace C here. Or sorry, not C, but I can use this circle to replace, say, D here. Okay? So from this circle, what is A equal to? We'll just solve for it. Add the B over. It's B plus MK. So you get B plus MK going in for the A, then times the C, then minus the B, and then what is D? From this circle, we'll just solve for it. Take the D over there, take the ML over there. It's C minus ML. So for this D, I can write C minus ML. What can I say that's equal to? Well, I can distribute the C through now, right? And the B through here. So that would be BC plus MKC minus BC plus, minus minus makes a plus, from kindergarten, BML. Okay, so you get that. Well, can I say that's equal to? Well, obviously these now cancel. And so I get MKC plus BML. Just these two terms are left. Well, can I say that's equal to? Well, obviously I can now factor out an M and say this is MKC plus BML. And so you just discovered that this difference is a multiple of M. Yeah? As long as you explain why that's an integer, you just shown that M divides this difference. But then by the definition 2 pages ago, that means they're congruent modulo M. And the theorem's proven. Okay, so let's say that and wrap it up. And it's an integer since all these were. Okay, so since K, L, C, and also B are integers. We know when we multiply and add integers, we get integers. So we know KC plus BL is an integer. Our usual statement, since all four of these are integers, K, L, B, and C, we know that their linear combination is. Okay, so from this equality, this bubble, we get M dividing this difference by the definition of division 3 pages ago. Thus, M divides AC minus BD. And so, AC is congruent to BD mod M. And that gives the theorem. That's the second thing. With that being said, these are homework problems, things to prove about divisions and modularity. It's in 4.1. And the problems are: And the problems are 5 to 12 all, 17, 18, then it jumps up to 40, 41, 42, 44, 45, 46, and 47. So that's the assignment for 4.1. These are asking you to prove things about divisibility and modularity. Remember, you got Theorem 1 and Theorem 5 to use as weapons. And yeah, we'll get your test back sometime soon. Okay? Maybe in the next couple days. Okay, with that being said, try these problems. Make sure you can do them all, just in case you're asked one of them on the next test. Okay, so have a good day. Stay safe.